opportunity to chair this session at QIQT2023. In the last 3-4 years, QIQT has made its own name because of this regular arrangement of the platform for discuss the ideas of quantum information and quantum technology from various directions. So today also, as usual, we have a very distinguished panel of speakers, and we will go through and we are very much excited to listen from all of them. So today's first speaker is Dr. Suranjana Ghosh, who is a senior research associate at IIT Patna. She obtained her PhD from PRL, Physical Research Laboratory, Ahmedabad, and she worked as a postdoctoral fellow at University of KwaZulu-Natal, Durban, and University of Camerino in Italy. She was awarded Senior Research Associateship by CSIR in 2011. She also received Young Scientist Project Award by DST Fast Track Scheme in 2011. Her research interest includes quantum information, quantum optics, and today the title of her talk is Quantum Precision Measurement in the Diatomic Molecular System. So let us welcome Dr. Ghosh for this session. Please, it's over to you, Dr. Ghosh. Thank you.
Okay. Thank you very much, Hoyan, for this nice introduction. I'd like to thank also all the organizers of QIQT, and it's my privilege to be, part of this summer school because I'm attached to this summer school since beginning. So it's a wonderful experience. Okay, let me first share my screen here. Is it visible from other side?
Yeah, it is visible.
Okay, nice. Okay, so today I'll be talking about quantum precision measurement in the diatomic molecular system. So here, precision measurement is a very active field. Basically, the field which we call the metrology field. And when we talk about the quantum precision measurement, it's much more challenging. And that is the field exactly it deals with, that is quantum metrology field. So here today,
hello, ma'am. Sorry
yes.
for interruption.
Yes.
Please put your slide in full screen mode.
It is in full screen mode only.
No, it is actually, we cannot see the full screen mode.
Okay, let me check. Actually, I have done it in full screen. I don't know why it is not showing from other side. Maybe let me unshare this and I'll share it once
that
more.
will be better.
Yeah.
Yeah, now it's fine.
Okay. Okay, fine. Fine. So, this is the topic, today's topic, this quantum precision measurement in diatomic molecular system. So I'll be mainly dealing with the precision measurement, or how quantum parameter one can measure with a very high precision. And mainly I'll focus for the diatomic molecular system in this study. So this is the flow of my talk. First, I will start with the property, which is quantum superposition. And there are some well-known states in the literature, that is Schrodinger cat state or compass state. These are all non-classical states. So I'll start with that because we are going to use those states. And then I'll discuss what are the Subplunct scale structures, because it has very prominent role in quantum sensing domain. And then different kind of approaches we have used for diatomic molecular system to enhance the sensitivity. The first approach is we will construct a coherent state, and then coherent state is nothing but a wave packet. Okay, so we'll see the system dynamics, and there are some interesting phenomena occurs which we call revival or fraction revival. So I'll briefly explain those phenomena and then see how this fraction revival phenomena, it plays a very important role to enhance the sensitivity, where this sensitivity limit will reach to Heisenberg limit. And the second approach is coherent control method. So we are going to use make use of this method to enhance again the precision. Okay, and this is another approach to find some application in quantum sensing domain. And the third one is rotational amendment to vibrational wave packet. So far we dealt with the diatomic molecule where we have considered only the vibrational states. So here actually we will look for some resources what can enhance the sensitivity. So here we will consider the rho vibrational coupling, and that rotational amendment will see is it possible to enhance the sensitivity using that property or not. And the fourth one is a photonated coherent state, which is very well known in the literature. So that basically we will see for the diatomic molecular system, if we can have this photonated coherent state, then what will be the application for this kind of non-classical states if we see the effect of photon addition, whether it will improve the sensitivity or not. And the last one is new kind of state, that is quantum tetrachotomous state. And very recently it is reported in the literature that they claim that these are very sensitive structures one can find and comparative to Schrodinger cat states, and it has many applications in quantum sensing domain. So finally I'll conclude. And okay, so let me start with this quantum superposition principle. So this quantum superposition, this nature is completely different what we see in our daily life. For example, in this macroscopic world, if I say that some object it is I'm holding here, and that is also there with you, then it's you can't accept the statement, right? So we always believe that the position will be particular, so it cannot be in a superposition state. But in quantum domain, we know that quantum particles, they behave completely different way and they show some varied behavior. One of those is a quantum superposition. So Schrodinger, actually, he tried to explain or describe it, and he used a thought experiment where he put a cat inside a box. It's a well-known story. Cat inside a box, and inside that box, there is a radioactive substance, and the mechanism is like that if the radioactive substance will decay, okay, so there is a hammer. That hammer will fall on a vessel, on a bowel maybe made of glass, so that will break the bowel, and that bowel is containing some poison, so that poison will come out and that will kill the cat. So that means if the radioactive substance, it will decay, so that means the cat will be dead. If not, then cat is alive. But that we only know if you disturb the system or measure the system, because this box is completely closed from outside. So if we don't see, we don't know whether it is dead or alive. So to know that, we have to measure or disturb the system. And otherwise, we will say that it's like in a superposition state. So that's the well-known thought experiment. So idea actually for coherent state in quantum domain, we describe with the optical coherent state, where these are the two coherent states, okay? The first one, we can compare with the live cat, and the second one with the dead cat. And in between, there are some, ripples. These are interference structures, some kind of oscillatory, behavior there. So that quantum interference structure, it plays very crucial role in quantum sensing domain, because these structures can be used to enhance the sensitivity limit. That basically we will deal here in our study for measurement of quantum parameters. So this is the field which exactly deals with that is quantum metrology. But there are certain fields also for this world people are working, for example, quantum computing, quantum cryptography, quantum communication. So all the fields are, it's contributing to develop the new technology, which is a quantum technology. And of course, these are all connected with the foundation of quantum mechanics. So for students, this is, they should first learn this, and then one can have specialized knowledge and can find some application as well for quantum technology. Okay. So how precisely one can measure the quantum parameters? So for example, if you want to measure any parameter, for any kind of measurement, it will have some kind of error. And to minimize that error, one has to repeat that measurement process or the experiment. And if we do a number of times, then we have to take average over there. And that error basically scales at 1/√10. That is the standard quantum limit one can have. This is the ultimate limit if you use the classical protocols. So one cannot go beyond that. But if we use some quantum properties, for example, this quantum superposition or quantum entanglement, so that this property can, beat this limit, and their kind of enhancement one can have, and this basically known as the Heisenberg limit. So √10 times enhancement is possible. So that's very interesting field, always working beyond the standard quantum limit. That is a very active field, and that give very high precision of measurement of any kind of quantum parameters. So exactly, these Subplunct scale structures, these are very well connected with this limit. So this is the first paper in Nature 2001. Zurek pointed out he actually found this for quantum version of a chaotic system, and he observed that these smallest regions, the dimension, it goes below Planck scale, it has some physical significance. And this later he modeled with the harmonic oscillator. See this right hand side figure, it's known as the compass state. So there are 4 coordinate states you can see here, and these are the 4 coordinate states, and at the central region there are some checkerboard pattern. So this is very small quantum interference region, and he described that these are the Subplunct scale structures, and they have a very good application in quantum sensing, because these are they have sensitivity which is at Heisenberg limited sensitivity. So this is the first work, and he gave a model using the oscillator system. Now we are trying to find this smallest structure, if one can find in molecular system or not. So this is okay, let me just tell you this. Obviously this dimension, as I'm saying already, that is a Subplunct scale structures. So dimension will go below the Planck scale. So it doesn't mean that it will violate the Heisenberg principle. Okay, so and also automatically we have a concept that if something exists below the Planck scale, that doesn't matter, or it doesn't have any physical significance. But this common assumption is false, and they are physically significant, and also they play a very crucial role. For example, if there is any kind of perturbation or disturbance or coupling with the environment, these smallest regions can detect fast that they can determine that this kind of perturbation is present. Or maybe if there is a weak force, it's a very difficult task to measure, and weak force can disturb the system, can displace, where the displacement may be of the order of Subplunct level, even though this dimension is very small. Then also these two becomes quasi-orthogonal. So that small, small interference region can distinguish these two states and can measure the corresponding weak forces as well. So these are the things. It's already he observed Zurek, and he mentioned that it plays very crucial role in Heisenberg limited measurement. So here there are different approaches we have studied for diatomic molecular system. So okay, let me tell you very briefly about this model. This is the Morse system, where we are considering only the vibrational motions, and the Morse potential, it looks like that, where you can see this potential, see this potential here, and this potential, D is a dissociation energy, beta is a potential parameter, and the corresponding eigenfunctions are given here, where zeta is a variable connected with the position, and then other parameters are there, energy, this is also connected with all other potential parameters. So this one can find, also check with the original paper of Morse. And then, so our target is to find a coherent state. And this Morse, it has finite number of bound states. So dynamical symmetry group is SU2. And so these are the generators which satisfied this algebra. So using that generators, we actually constructed the coherent states. But for the, this was first introduced by Schrödinger when he tried to describe the non-spreading wave packet for harmonic oscillators. But there are different, 3 definitions, and one is annihilation operator coherent state, then the Perelomov coherent state or displacement coherent state, and another is minimum uncertainty coherent state. So these 3 are same for oscillator system. But for other physical system, it's not. So there are different approaches to, construct the coherent state. Even the finding the generator is a very difficult task. And so there are different approaches to find the generators, and it's not very simple like A dagger algebra. So it's finding that generators, one can, construct different kind of coherent state. So here, actually, we have constructed a Perelomov type coherent state, and you can see this chi is the coherent state. And it's a kind of, displacement operator is operating on vacuum state. And finally, there's a lengthy calculation. I've just written here the final state, which is a superposition of few eigenstates of Morse oscillator. And D is the weighting factor. So here, coherent state is nothing but a wave packet. So it's a well-defined wave packet. And so if we have the time evolution of that wave packet, so we'll see the system dynamics. Here, psi is a time-dependent wave packet, and you can see the phase term, exponential term. So all this calculation I'm doing here in atomic unit, so h bar is 1. So I'm not written here. So these n number of states are contributing to form the wave packet, and Cn is the weighting factor. So we have a time-dependent wave packet here. Now, the system dynamics for quantum system, it basically depends on how the energy term is dependent on the quantum number. For example, classical example is that planets are reviving after their, classical time periods, right? But for quantum system, if we have a very simple kind of energy dependence, for example that linearly, if it is dependent on that quantum number, where En is alpha n, alpha is a constant parameter, say. So then the system will revive when the time will be 2 pi by alpha. So that we named as T classical, because initially what will happen, few cycles it will behave like a classical particle. There will be not much change, but after a few cycles of that, dephasing will start. So initial dynamics will be dominated by this TCL. Then dephasing starts, and then it will come back to initial state again. So for linear dependence, for example, for the oscillator system, it's one of the example where it will revive after their classical time periods. Now, if you have a bit complicated energy dependence, if it is having also quadratic dependence, alpha n plus beta n square, where beta is another constant, then extra phase, okay, it comes from this beta n square term. So around t equal to 2 pi by beta, this phase term will be again 1. So this term will be again 1. sorry, my battery, just a minute, 1 minute. Sorry, actually my laptop's, this adapter is connected, still it is showing battery is low. So I think it's fine now. Can you hear me?
Yeah, yeah.
Okay.
Yeah, please go on.
Yeah. Sorry for the disturbance.
No problem. Yeah, please
yeah.
take your time.
So, yeah, so I was there. So this quadratic dependence I was discussing, where another time scale one can define, that is T revival. So it's coming when energy, it has quadratic term. So in this case, we have to wait for a longer time evolution, because initially what will happen, it will revive after their classical time periods, then dephasing starts, and then finally, it will regain its original state at time t equal to T revival. So for this kind of energy dependence, one can define these two time scales. But we don't find all the physical system which has this kind of, quantum number dependence. For other cases as well, one can see this revival dynamics. But in that case, with some condition, one can expand the energy in Taylor series and can, find these linear and quadratic terms, and one can define this time scale TCL and T revival. So if we see this time evolution for a long time, before reviving, after their revival time scale, we'll see that the initial wave packet, it will split into mini subsidiary wave packets. So that's very interesting because at some fractional revival of fractional time of revival, it will split into mini wave packets. And that phenomena is known as the fraction revival phenomena. So there are some mathematics here. One can see exactly how many parts and what time it will break. So using that mathematics, one can explain as well that, for example, this non-linear term, one can write as using this discrete Fourier transform as a linear term, and can find that the periodicity, it will satisfy some condition. And when L is equal to S, for example, 1/3 of T revival time, then S will be 3. And in that way, one can find that L will be 3 here. So there will be, P will go up to 3 minus 1, 2. So there are 3 terms, 0, 1, and 2. The initial wave packet and 1/3 of T revival time, it will split into 3 wave packets. Similarly, for the other condition, when S is an integer multiple of 4, for example, if S is 4, L will be 2. So there will be 2 terms, P equal to 0 and 1. So initial wave packet will split up into 2 wave packets at that time. So that's very, nicely one can see, one can check with this mathematics also. And there is a well-known paper by Aberbrook. One can see in the literature. He explained very nicely. And okay, so here, this is a movie I have taken from Stroud's web page. This is for Rydberg wave packet. It's a very nice movie. One can see that initial wave packet, it was initially localized, then dephasing starts. And then after a certain time, so it's going to revive, but in mini wave packet. That's exactly what I mentioned about the fractional revival. So it is, see here, it is, it breaks into 4 wave packets. So while this number one can find from this above equation, and also the corresponding amplitude one can see also. So at different time, the initial wave packet, it splits into mini wave packets. And then if you wait for a longer time evolution, when the revival time comes, at that time, it regains its original state. That is called the revival. And at 1/4 of T revival time, it should break into 2 wave packets. See this one. Here it is there are two wave packets. It's very similar to Schrodinger cat state. So in phase space, it looks like this. These are two wave packets, like a dead cat or live cat, and in between some interference ripples are there, right? So so that's the idea I'm going to use here for molecular system. We have already this coherent state, and this is the weighting factor, which it depends. There are coherent state parameter also there, so one can have so that freedom. One can change that coherent state parameter and can involve different kind of vibrational level as well. And this is the system's energy. So M is vibrational quantum number, and depending on that, see here there are linear as well as quadratic terms. So one can define these two time scale, TCL and T revival, right? So now this is for a particular value of alpha, and the left one is showing that which levels are contributing. So one can see these lower levels of more system they're contributing, and it is almost peaked around n bar, it's 5, and the corresponding initial wave packet is well localized here, right? So one can choose the initial wave packet accordingly, and to condition to see the fraction revival, the initial wave packet should be very well localized. So this is different probability distribution. Okay, we just check for different parameter values for coherent state, and these are the different probability distribution. One can have different initial wave packets and can see their time evolution. So for a particular value of alpha, here we have chosen alpha is equal to 1.4. See, the first one is showing the initial wave packet. Figure B is very complicated. It's not clear exactly what is happening. Basically, this happened at 1/8 of T revival time. It should break into 4 wave packets, but in coordinate representation, it's not clear. And for C figure, it is for 1/4 of T revival time. So it's very similar like Schrodinger cat state, 2-way breakup, one can see, but these are this is for asymmetric potential. So 2 wave packets are not similar, and you can see the potential effect also. And then last one is half revival time. It's reviving, but slightly shifted. So these are all in coordinate space. Here now we move to the phase space to see what is happening exactly, and what are these quantum interference structures are there or not. So there we calculate the Wigner distribution function, which is a very useful tool to see the quantum interference phenomena, and and it shows the negative regions where it has direct evidence of quantum behavior. Okay, so for phase space structures, use this Wigner distribution, and these are all same shots they have taken at different time. So T equal to 0 initial coherent state, and then 1/4 of T revival time. You can see this is 2-way breakup, and in between some positive negative ripples are there. These are quantum interference region. And at 1/8 of T revival time, it's as we have taken very lower level of the potential, the total phase space support is very small. So initial there should be 4-way breakup, 4 coherent states, but they are not very well separated. There are 4 coherent states, but in between, at the middle portion, one can see some negative positive regions, and these are quantum interference regions. And the dimension, what Zurek claimed that for this kind of state, the dimension should be below the Planck scale. So we have checked here also for 2 cases, alpha is equal to 1.4 and alpha is equal to 2.5. Here is the total phase space support, and small a denotes the Subplunct dimension. And for compass state, for example, this when we saw that 4-way breakup, which appears at 1/8 of T revival time, we checked the dimension. The Subplunct dimension is coming below 1, and that is very small. For 2.5, when alpha is equal to 2.5, it's 0.39, and when alpha is equal to 1.4, it's 0.18. So that's the first observation of this Subplunct scale structure in molecular system, diatomic molecular system. And of course, it has many application in quantum sensing domain. Now, next is coherent control method. If we use this method, is it possible to improve the sensitivity limit or not? So coherent control method, it started long back. There are seminal papers by Paul Brummer and Sapiro. So it started long back, and then I think Fleming, he first time mentioned about the wave packet interferometry. So that idea also we are going to use here, where 2 femtosecond pulse are used and their phase is locked, and one can control their phase and can have control over the quantum interference structure. So that's a very challenging task. And okay, so one group in Japan, they has been working with diatomic molecular system, and it's a very good work. They published where they experimentally observed these quantum interference ripples, and using this wave packet interferometry for the iodine molecule. And it's another paper also, they have designed also quantum carpet experimentally, and it's a bit different from usually what happen in wave packet interferometry. They prepare 2 wave packets which moves in a direction which is in the same direction, so the overlap is stable. But here what they have done, where these 2 wave packets, when they're using a double pulse scheme, using 2 femtosecond pulse, it will create 2 wave packets, but these 2 are counter propagating wave packet. So when they cross each other, that time only the overlap, it exists, and that is only order of, not more than 100 femtosecond. So the time duration is very short, and also the spatial resolution very high, that is picometer. So with this resolution, they experimentally first time describe this quantum carpet for iodine molecule with their experimental setup. So based on this setup, actually we did this work with these experimental values we have taken, and also work on this iodine molecule. So the idea is that we have used these 2 femtosecond pulses, where if you have a control, there is a relative phase between these 2 optical pulses. So if you can control their phase or amplitude, so directly you can control the phase and amplitude of the corresponding quantum wave packet, molecular wave packet. And so if you have control, then we can also control the quantum interference structure. So here we considered an initial wave packet, which is a combination of 2 wave packet phi1 and phi2, where phi1 it includes odd levels only, and phi2 even levels only. And theta is a parameter which that is the relative phase. It's coming from femtosecond pulses. Okay. So this is a phase diagram. Here it shows that how the even part and the odd part are contributing. Okay, when theta is equal to 0, only you can see that odd part is contributing. When theta is equal to pi, even part is only contributing. And when theta is equal to pi by 2, both are equally contributing. So in other cases also there is a competition. So it's like how individual wave packets they are contributing at a particular time, one can find from here. And then we'll see the time evolution at, mainly we will focus at 2 particular time. One is 1/8 of T revival time, because at this time we already found that this Subplunct scale structure exists in a compass-like state. So we are interested here what is happening in this case also at 1/8 of T revival time. And another is 1/16 of T revival time. So it's like a combination of 2 imprinted compass-like states. So that would be much more interesting to investigate, exactly what is happening at this time. Okay, so see, these are Wigner distributions. The first one is theta is equal to 0, where you can see Schrodinger like cat state. And in at the center also, these are the quantum interference structures. And then next is when theta is equal to 5, we are changing theta all these snapshots are taken at a particular time, that is 1/8 of T revival time. So only parameter which we are changing, that is theta. So changing that theta, we can have different kind of quantum superposition here. That's very interesting. So when theta is equal to pi/4, see the even parts, it start contributing. When theta is equal to pi/2, both even and odd parts are contributing. You can see that in figure C. It's very similar to like optical, compass state, but asymmetric effect is there still. But one can see this looks very similar to that north, south, east, and west kind of state. And at the middle, one can have checkerboard pattern, Subplunct, quantum interference structures. And when theta is equal to pi, it's again a cat state, but it is localized in momentum space. So at a particular time, here we have freedom, and changing this theta, one can have different kind of superposition states and can probe, a different kind of sensitivity limit. This is for 1/16 of T revival time. So initially, this is again for theta is equal to 0. It's not exactly like compass state, but it is rotated one. And when theta is equal to pi/4, even part starts contributing. Theta is equal to pi/2. It's a combination of two compass-like state. And theta is equal to pi. It shows again the compass-like state at this time. Okay. So now we want to see whether they are really, contributing in quantum sensing or not. And we have calculated here the Subplunct dimensions for different values of theta at time 1/8 of T revival and also 1/16 of T revival. And we saw that when theta is equal to pi/2, it shows the maximum sensitive structure when time is 1/8 of T revival time. And when theta is equal to 0, it shows the maximum sensitive structures that time is 1/16 of T revival time. And the corresponding figures are this. It looks like this. So this is very interesting because using this coherent control method, one can enhance the sensitivity limit. And not only that, this compass-like state, one can easily find in the fraction revival, which time is 1/8 of T revival time. But here, using this wave packet interferometry for a shorter time scale, for example, 1/16 of T revival time also, one can have these maximum sensitive structures. And that, of course, help to avoid the decoherence, if we can observe at a small time scale as well. So that's the application of this coherent control method, what we found for the molecular system. Okay, now it is enhanced quantum sensitivity due to rotational amendment. So far we discussed about the vibrational motion only. Now if we consider the rotational part as well, so in that case it's a bit complicated because when you consider the rotation, it becomes three-dimensional, and the phase space scenario will be six-dimensional. So a bit complicated. So we actually we started with a very simple model, that is rotating Morse model, and it is in one dimension itself. One can capture the coupling effect. So this potential looks like that, and you can see the potential for very small coupling. This value of J, the potential is changing, and accordingly the system dynamics will change. So here also I have not included all the mathematics here, just I'm telling briefly that we started with the coherent state, and you see the blue line, it is showing when there is no coupling. Okay, and at 1/4 of T revival time, the wave packet, initial wave packet is peaked around n bar is equal to 10 here. And the initial wave packet, when you see the system dynamics, the 1/4 time, it will split into two wave packets. That is what actually the blue color is showing. Now, if you couple with the system, rotational coupling is present, then you see the scenario is changing. These two wave packets is coming closer, the red one. And the black one is completely different. You can find some kind of oscillatory behavior. So changing this coupling parameter, one can change the system dynamics, because all this observation is happening at a particular time only. Now we check the Subplunct dimension, how it is changing with this coupling parameter. So with J, we find that this dimension, it's becoming like oscillatory, it's showing behavior, and all these minimas are showing that maximum sensitive, regions. So this first one, when J equal to 0, the first figure is showing, and now the first minima is showing the maximum sensitive region, and the corresponding state, it looks like that. Okay, this is for cat state. Now for compass state, the initial one is showing when J equal to 0, and these are the minimas which shows the maximum sensitive structures, and the corresponding state looks like that. So we made a comparison between these two states, and we found that the maximum sensitive structure one can find in compass-like state as well, when coupling is there, J is equal to 64, and it enhancing the sensitivity in this case also. Okay, next photon-added coherent state. So photon-added coherent state, it is well known in the literature as Professor Agarwal and Tara. There's a paper long back for an optical system. He mentioned about this. So for addition of photon, this coherent state, it becomes non-classical state. It shows some quantum properties, subposition statistics or squeezing, all those things. And here you can see this figure I have taken from Wikipedia. See this, the coherent state is alpha. When we added the photon, this is the Wigner function. You can see this function is showing the negative region, which is a direct evidence of quantum nature, right? So this idea, it is already known, and there are some experimental evidence also in the science paper, one can see it. Idea is we want to see what is happening when you consider non-classical states, right? So for optical states, see the first figure is a cat state, and the second one is showing photon-added cat states. But as a whole, we can't distinguish these two states, right? But this basically leads a phase shift at the origin. If we see the middle interference region, for example, here, so this oscillation, it has shifted. The positive one, it falls on the negative one when we have taken the photon-added cat state. So that's a, for optical system, one can see, and there is a paper recently by Professor Panigrahi also for compass state. They found that there is a diagonal shift for compass state for this photon-added cat state, right? So here idea is we want to see for more molecular system. And for molecular system, already I've described how to get this coherent state. And here actually we found the photon-added coherent state, while we have added 1 photon or 2 photon. So in generally, we can consider Q number of photon, and this is the analytical result one can have. And if you go to phase, you see for photon addition, how these things are changing, okay? So first is 1 photon added, second one is 2 photon added, and third. So this way, if it goes on, so here, okay, let me see you this small animation. You can see with the addition of photon, the individual coherent state, this goes far apart, and the intermediate, quantum interference structures becoming, very, very fine structures are coming out with the addition of photon. So obviously, it's showing some, enhancement of sensing. This is for compass-like state. In molecular system, we added photon 1 by 1, and again you can see this. It will change how this system dynamics. So individual coherent states is going far apart with the addition of this photon, and the smallest region, the dimension is going down. These are becoming very small and small. So that is what actually we calculated the variation of the Subplunct dimension with a number of photons added. So we saw that there is a, the dimension is going down with the addition of photon. So that means sensitivity is increasing. Okay, so that is for cat state. As well for compass state, we also checked this the addition of photon. This again, the dimension is going down, and it improves the sensitivity limit. So that's a new result we found for molecular system as well. Okay, so next is special kind of state, that is quantum tetrachotomous state. So this state, it was recently reported in the literature by Barry Sanders group. They said that there are 4 coordinate states and they will be situated on a line. Okay, so a pair of 2 Schrodinger cat states, and then what will happen? They said that it exhibits much more richer phase-phase structures than a Schrodinger cat state. So it's very interesting to see. They have found for optical coordinate states. So these are schematic diagram I'm just given here to show how does it look. So here these are a pair of cat states. Okay, so these 2 are individual coordinate state. Okay, they are far apart, and there will be some quantum interference region. So for a single cat-like state, one can find, of course, at the middle the oscillatory these fringes, but there are 4 coordinate states, so there'll be much more ripples. So that they reported in 2019, and they basically studied for different 3 cases. So our idea is to find first time in the molecular system. So that let me just tell you, this is different from what Zurek mentioned, that is compass-like state, where these 4 coordinate states, these are situated on a circle. But here scenario is different. They are on a single line, right? So we already, there are several works I have shown already. That compass state, it will show that nice checkerboard pattern interference fringes at the same central region. So here you can see this interference pattern is coming because of this cat state. Here also it will also come, but at the central region there will be these diagonal pairs, and when they overlap, okay, so that gives them most sensitive region, that is a Subplunct region. Okay, so this is for compass-like state, what Zurek mentioned, but this tetrachotomous state will be different. They will be on a line, single line, and this looks like that. The interference pattern will come. So it's a schematic diagram, but this middle portion, these fringes will be much more sharper. Okay, so that we'll see later. In a physical system, we are also going to observe this state. Okay, so this tetrachotomous state, here we consider, again we are using the wave packet interferometry, and here 2 femtosecond pulses are required, and we will create 2 wave packets in a different 2 electronic states, and then there will be some kind of delay between these 2 pulses, so that our observation time will be such that at that time both the wave packets, okay, it will split into 2 wave packets, and that will happen when time is 1/4 of T revival time. So our observation time is 1/4 of T revival time for both the wave packets, and it's a kind of state when we'll see the system dynamics where 2 wave packets are created and their phase can be controlled using this wave packet interferometry method. So using that, we have considered the first case for the oscillator system, that 2 coherent states in a single cat state, they are very closely spaced. Now for the molecular system, we have found similar kind of state. This is all tetrachotomous state. They all are lying on a single line, but as these are not symmetric ones, so 2 coherent states are it doesn't look similar, but there are 4 coherent states one can find this way on a single line. So we have taken very lower level of modes, so they're very closely spaced, and the initial wave packets are peaked around m bar is equal to 5. Another also case we consider where they are little far apart. So in this case, again, it looks like that. Okay, so if you change, changing the coherence parameter, we can pick to the higher levels, but we can't go very, to the upper levels because the enhanced effect is there. So if we change a little bit, one can see comp-like state also. But anyway, here we have taken, this is another case where it is peaked around in m bar is equal to 16. And again, one can find this kind of structure. So now in phase space, it looks like that. So in phase space, the first one, it looks like, see, the left one is showing the, single Schrodinger-like cat state, and the right one is showing the another Schrodinger-like cat state. And in between, one can see very sharp fringes. These are all interference patterns are coming up. And for the next case also, we will see here. Similar kind of very fine fringes one can find, and one can easily see that, it enhancing the sensitivity, because for if we compare with a single Schrodinger cat state, if we have this kind of state, tetrachromatic state, that will enhance the sensitivity. So that's the idea. Actually, we started with the optical system. It looks like that. But for a physical system for diatomic molecule, we found this tetrachromatic state. And obviously, it will have some very good application in quantum sensing domain. But it's very difficult to handle with the molecular system, because it requires very, very, numerical task, and it takes a long time to get a single figure. So that's the final. Here I'm stopping here, and this is my conclusion. So what we have found that we basically discuss about different kind of mesoscopic superposition states. Okay, so mainly we emphasize on Schrodinger cat states or compass-like states for diatomic molecule. And then we saw that for diatomic molecule also, one can have the Subplunct scale structure, which is very, it has Heisenberg limited sensitivity. And then we move to the coherent control method to enhance the limit. And then the rotational amendment, which is also, it shows that this limit, one can beat this limit. And photonated coherent state we discussed and showed that it also plays very crucial role in precision measurement. And finally, the special kind of state, this quantum tetrachromatic state, we found in diatomic molecular system. So maybe these are having some good application in quantum sensing domain or high precision measurement, because it deals the domain which is beyond the standard quantum limit. So that's all, and thank you very much for all of your attention. I can't hear you, Anne.
Thank you. Sorry. So thank you, Dr. Ghosh, for this wonderful lecture. And I think this actually touches starts from the very elementary ideas to the recent research advances. So I believe this is very much enriching for the students. And now the session is open for question. So please, if you have any question, please come up and ask.
Hello, ma'am.
Yes.
Audible?
Yeah.
Okay, so like, ma'am, the number of states which we get at the depth of the potential curve, the Morse potential curve. So those states, are they coherent?
See, these are individual eigenstates, right? These are individual eigenstates. You are talking about the individual states. These are eigenstates. So coherent means, if you use any, do any coherent pulse, for example, laser pulse, then only few states, depending on the bandwidth of this laser pulse, okay, few states it will be excited, and they will be in a coherent mode. That is why actually you can see this wave packet, right?
Yes, ma'am.
Any other question?
Let me ask one question.
Like the number of like excitation, the number of wave packets which we will get, it depends upon the excitation.
Yes, of course.
Okay.
It depends on the frequency of the laser pulse. Okay, so that will decide which other level will be excited.
Okay, thank you, ma'am.
Yeah, I have a question.
Yes.
Yeah,
sir.
sure, Professor Manik. Right?
Suranjana, you mentioned about the Heisenberg limit, right?
Yes.
With, and then, first question is, why is it that Heisenberg limit is reached, with 4 of them? Secondly, what more can you do? If we have put more, what will happen? We have seen that also. Now it is coming to my mind as a curiosity, because Heisenberg limit is achieved the moment you go to Packet state, right?
Yes.
1 by n. Now beyond that, what happens that I'm just curious.
So your question is beyond Heisenberg limit?
My question is that we cannot go beyond Heisenberg limit.
Yeah,
right?
that is not, that is the ultimate limit.
So therefore, if we superpose more, what would
Okay.
happen? We have done that work, but it is not coming to my mind right away.
Okay. See this sensitivity, it has some limit, but we are not reaching the ultimate limit. We are going close to that limit. So if you are
Okay.
using, for example, cat state, you have these ripples which have high precision in a particular direction, not in both direction X and P. And when you are using this compass-like state, we are increasing the coherent state numbers. Okay, so then only the sensitivity limit it is increasing. So this way, one can add more coherent states and can see how this sensitivity or precision can change. So there is a certain limit one can reach up to that, not beyond that. So that way one can see also general generalization of this cat state superposition. So that work also we have done, and it is also we have communicated in a journal. So very nice result we also got for that case.
Thank you, Professor Panigrahi. Any other question, please?
Can I ask a question?
Please. Yeah,
Yes.
please.
Yes.
Thank you for your talk.
Yeah.
I think my questions are related with continuation of Professor Panikar's question. So which parameter one needs to calculate to quantify whether state can improve quantum sensitivity or precision?
It depends on the system. For example, see here for our case, as I already shown for molecular system. If I start with my first work where we have constructed the coherent state. See, if you change the coherent state parameter, it involves different kind of levels of the Morse potential. And if you consider the higher levels of that Morse potential, the initial wave packet is very sharp, well localized. And you will see when it is breaking into many subsidiary wave packets or coherent states, they will be, when the phase-phase support is large, right? They are very far apart. And the dimension of the smallest region will become very small. So it depends here that what kind of states are contributing, or what is the phase-phase support. So it depends on this phase-phase support as well. If support is very high, then obviously the dimension of the smallest region or the sensitivity, it will increase.
Okay, thank you. On your slide, quantitative analysis of Subplunct structures. I think you have calculated some parameter, right?
Yes, that is h bar squared by that is A, that classical action phase-phase support.
Yeah. So what A is meant for?
It's a delta X, delta P, this uncertainty product. For a system, you can calculate the expectation values of AX and P, and from there one can find delta X and delta P. So that's a product of these two. That is the total phase-phase support, delta X, delta P. So that is classical action.
Okay. Okay. So, but you have used this parameter to quantify whether state can improve quantum precision or sensitivity, right? Am I right?
Yes, yes, because the Subplunct dimension, that you can go through that paper, the Zurek's paper, Nature paper. He, for the oscillator system, he actually mentioned it, the dimension of that Subplunct, these structures will be order of h bar square by this A. A means the classical action. For other physical system, you can see other paper also. I have not mentioned all the works here. Another paper we have published in Physical Review, that is on postular kind of potential, and we have proved it that for other physical system also that law valid. So that is the law that this dimension will be order of h bar square by classical action A. So that is also valid for other physical systems. So in molecular system also we checked for in another paper that one can find this dimension as well using that equation.
Thank you.
Thank you very much. I have a small question.
Yes.
what I realized in the later part, in the last part of your talk, you are talking about a linear system instead of the compass-like. But in the compass-like, it's very easily I can see the checkerboard structure and the sensitivity. As you have mentioned, it has a high sensitivity. Now, in the linear system, how we will get higher sensitivity?
See, this I made comparison with the Schrodinger cat state. There is a
Yeah.
statement you can see. I have written there that already they have mentioned these structures, this tetrachromatic state. Yeah, here you can see that they exhibit richer phase space structures than a Schrodinger cat state.
Okay, fine. So it is not better than the compass one.
It depends actually. It depends.
Okay.
You can have better resolution in a particular direction. For Subplunct scale structure, you have this resolution in both the direction X and P. But
Okay.
for here, suppose you need something in the in momentum direction only, or in position direction only. There, this structure, this state will be very useful because in a particular direction, for example, this is the X direction. Along that direction, you have much more, better resolution, even compared to compass state also.
Okay. So, any other question? If not, let's thank Dr. Ghosh for this wonderful talk, and we move to the next talk.